Good evening everyone. Can anyone please confirm whether am I audible or not? I hope my screen is visible to all. I am Riya Tapwal doing PhD under the supervision of Professor Sudeep Mishra at IIT Kharagpur in the Department of Computer Science and Engineering. Today we are here to discuss the topic of week 9 and after that we will discuss the question of week 9. So today we are going to discuss majorly three topics, that is your OpenStack, second one is your sensor cloud and third one is your fog computing. So first of all we will discuss about OpenStack. Now what is OpenStack? So OpenStack is an open source software which is used to create your cloud infrastructure. It is launched as a joint project by NASA as well as your Rackspace Hosting in 2010. There are various companies which are contributing to your OpenStack, such as your IBM, Cisco, HP, Dell, VMware, Red Hat. All these companies are contributing to your OpenStack. So these are suggesting or making changes to the code. And if those changes are agreed to everyone, then those changes are done to the OpenStack. So these are the various versions which are available in the market, and the most recent version of OpenStack that is available in market is Z, that is your ZED. So it will be launched in October 2022, and after that you can use that version. So now this diagram is showing the various components of OpenStack. So various components of OpenStacks are Horizon, Nova, Glance, Swift, Neutron, Cinder, Heat, Ceilometer, Keystone. Now one by one we will discuss that what are the functionalities of these different components in OpenStack. So first one is your first we will discuss about Horizon, and after that we will discuss about other components. So Horizon is the GUI of your OpenStack through which you can access all the other components. Okay, so it provides the overview of all the other component as it is the dashboard of your OpenStack. Now the second component of OpenStack is Keystone, which is responsible for providing identity service. So all the authentication and authorization of users are done with the help of your Keystone component. Third one is your Swift. So Swift is a storage component which provide you object storage and helps in storing data safely, cheaply and efficiently. Fourth component is Nova. So Nova component is responsible for providing you computing services, with the help of which you can run or launch your instances over your OpenStack. Next one is Glance. So as the name suggests, it is related to your image. So it provides image services to the user. It is helpful in discovering, registering and retrieving the virtual machines. With the help of snapshots also, you can discover, register and retrieve the virtual machines. Next component is Neutron. So Neutron component is responsible for providing networking services to the user. It enables the other services to communicate with each other, which are also helpful in making your own network. Next component is Cinder. It is again a storage component, but it provides block storage and also responsible for virtualizing the management of your block services. Next component is Heat. So Heat is responsible for providing orchestration. Orchestration means the automation of various services which are available, which are provided by your OpenStack. So Heat is responsible for that. Next component is your Ceilometer. So Ceilometer is responsible for billing, providing you the services which you want to use, and it also tell that for how long you, it also provide the bill of the service by checking that how long you are going to use that particular service. Wait, some people wants to join. Now next topic is your sensor cloud. So as the name suggests, sensor cloud. So is sensor cloud is an integration of your sensors and cloud? No, it is not just an integration of your sensors and cloud computing. It is also not dumping of your sensor data to your cloud. Then what exactly is sensor cloud? So sensor cloud is the concept of virtualization of your sensor nodes. As we have studied in cloud computing that various resources are available on the cloud, and from that pool of resources we can access the resources which we want to use, and for the particular amount of resources we have to pay. So similar is the concept of sensor cloud. So in case of sensor cloud, various sensors are present and we can access the sensor which we want to use, and on the basis of sensor which we are using and the amount of time for which we are using that particular sensor, we have to make the payment. One sensor can appear as many because one particular sensor can be used by multiple applications. So all the applications which are running may think that we are using different sensor, but in actual we can use one sensor which can perform the functionalities in various applications. Okay. Now next is virtualization concept. So as I have discussed that your sensor cloud is the concept of virtualization of your sensor node. So what exactly is virtualization? So in virtualization, one computer host may appear as many computer of virtual machine. It is responsible for improving the throughput and cost by using physical resources as a pool from which virtual resources can be allocated. So what are the various benefits of using virtualization? So virtualization is responsible for the sharing of resources. Many applications can share the resources which are available in the pool. Next one is encapsulation, then independence. All the applications which are running are independent of each other. They are not aware of the other applications which are using the same sensors. And next one is your portability. So virtual machines can be migrated from one place to another. So these are the difference between your wireless sensor network and your sensor cloud. So in case of your wireless sensor network, the ownership is with your wireless sensor network user. However, in case of your sensor cloud, it is with your sensor owner. Deployment is with in case of WSN, it is with WSN user, and in case of sensor cloud, it is with your sensor owner. In case of WSN, all the roles are played by your WSN user. However, in case of your sensor cloud, ownership and deployment are done by your sensor owner. Redeployment and maintenance are done by your SCSP, which is responsible for all the managerial tasks, that is your redeployment, maintenance and overhead. It is responsible for managing all the services which are going on your sensor cloud. And third one is last one is your usage. So end users are going to use all the sensors which are available in your sensor cloud. See, this figure is showing the difference between your conventional wireless sensor network and your sensor cloud. So in case of your conventional wireless network, there are a set of sensors whose data are used by the wireless sensor user. However, in case of your sensor cloud, many users or many applications can use the data which is provided by the set of sensors. Okay, so with the help of virtualization, all the different applications can use the data which are provided by these set of sensor, and these applications are unaware of the other applications which are also using the same data. Now, what are the different actors that are involved in your sensor cloud? So this figure can show that what can be the different actors actually. So one will be your end user who are going to use your data which is provided by your sensors. Second will be your sensor owner. So sensor owners are the person who are going to deploy their sensors, right? And third one is your SCSP. So it is your sensor cloud service provider. So this actor is responsible for managing all the services which is provided by your sensor cloud. It is also responsible for the billing, that how much bill we are going to propose for particular sensor, how much we are going to bill for a particular amount of time. All these things are managed by your SCSP. Now this is the architecture of your sensor cloud. Here we have set of end users which are going to use the data of your physical sensors with the help of web portal or the interface. And here is your SCSP, which is responsible for managing all the activities which are going on your sensor cloud, such as your pricing, caching, composition, management, virtualization. All the managerial activities are done by your SCSP. And the third layer is your sensor layer, and these sensors are the physical sensor which are deployed by your sensor owner. So there are various sensor owners which will deploy their sensors in the sensor layer, and further the management of these sensors are done by your SCSP, and the set of end users will further utilize the data of these sensors. Now, what are the different management issues that we face in your sensor cloud? So first one is optimal composition of your virtual sensor nodes. That how many sensor nodes are we going to utilize for a particular application, right? Second one is your data caching, and third one is your optimal pricing. We will discuss all these three in detail. Now the sensor cloud view. What actually the real view of sensor cloud is, and what end user are going to see. We will differentiate between those two views. So in case of your user organization view, your user are only able to see your browser interface with the help of which they can access the sensor cloud. So through that browser interface they are going to log in, and after that template display will be shown, and the user will select the template, and further that the user can access the data and or fetch the data from the sensor layer. However, in actual, there are various processes that are taking place in between. So here you can see that in real view, with the help of web portal, template specification. First of all, user login is done. After that, template specification is done. Once template specification is done, then various activities such as your XML interpretation, dynamic scaling, on-demand physical sensor scheduling, vast data storage, and specialized processing, energy management, and various other activities will take place at your sensor cloud. And then on the basis of these activities, data is fetched accordingly from your sensor, and then that data is provided to your user with through your web portal again. Now virtual sensors. So efficient virtualization of physical sensor nodes are required in order to fulfill the requirement of various end users. An optimal composition of virtual sensors. that which kind of sensor we are required in order to fulfill the needs of a particular application, how many sensor we require to fulfill the need of particular sensor. All these things we need to consider. So in order to consider those situations, there are two scenarios. In order to consider the efficient virtualization of physical sensor node and optimal composition of your virtual sensor, there are two scenarios. First one is all the sensors lie in your same geographic region, and the second scenario is the sensor nodes are spanned across many multiple regions. So first of all, we'll consider the first scenario to form your virtual sensor. So in case of your first scenario, homogeneous sensor nodes that are present in the same geographical boundary will form one particular virtual sensor which is going to fulfill the need of particular application, right? However, in case of second scenario, different heterogeneous sensors are taken from different locations, and the combination of those sensor or the cluster of those sensors will form one particular virtual sensor which is again going to solve the or fulfill the need of particular application. Now, why the composition of virtual sensor is required? Since the sensor nodes are resource constrained devices, one sensor node cannot fulfill the need of particular application, therefore we need to cluster these sensor node. After that, there is dynamic change in your sensor conditions, so in order to prevent that, we need a combination of sensors. Then third one is the composition of virtual sensors are non-traditional. Now next topic is your dynamic and adaptive caching mechanism, that how you are going to cache your data near to your end devices. First question is why we need to cache the data of your sensor nodes. So this dynamic and adaptive caching mechanism introduces internal and external caching mechanism which ensure efficiency in resource utilization. It is also flexible with varied rate of change of the physical environment. Now, why caching in sensor cloud? Why there is a need to cache data in sensor cloud? See, in case of sensor cloud, consider a scenario that where the data is not changing, the data which is captured by your sensor is not changing very frequently. For example, your weather data, it is not changing very frequently, right? So it is wastage of resources if we continuously fetching if we are continuously fetching the data from the sensor. So in order to prevent that, it will be better to store the data near to your end devices rather than fetching the data from your sensors every time whenever we need, right? And after a regular interval of time or on the request of user, we can fetch data from your sensor cloud, so from your sensors. So this will prevent the wastage of resources, so such as the bandwidth which is required to fetch the data from the sensors, or the power of your sensors also. So different kind of resources can be prevented from being wasted. Now the next topic is external and internal caching mechanism. So in sensor cloud, two mechanisms are introduced, that is your internal and external caching. So first one is your internal caching. So internal caching or internal cache is responsible for handling the request from the end users, and it take decision whether data should be provided directly to the end user from the cache, or there is a need or there is a requirement to recache the data from the external cache. Okay, and the second type of cache is your external cache. So external cache is for every particular amount of time or certain interval of time, In case of your external cache, we need to fetch data from your sensor and store in it in your external cache. Then few data are used to be transmitted to your internal cache. Then from your external cache, few data will be sent to your internal cache. So the size of your external cache is more as compared to your internal cache. These two diagrams are showing the architecture. So this is first diagram is showing the architecture. Then this is the existing architecture of your sensor cloud, that is without your internal and external cache. In existing architecture, whenever a different application wants the data, we need to fetch the data from sensors. So in this case, the wastage of resources will be done, because every time bandwidth is required in order to fetch the data from large distance, that is from your sensors. However, in case of your cache enabled architecture, we just only need to fetch the data either from your internal cache or external cache. So bandwidth utilization will be less, right? So in this way, your internal and external cache will prevent the wastage of your resources. Next topic is your dynamic optimal pricing for sensor cloud infrastructure. Okay, we have studied about your caching. Now we will study that how the pricing will be done, so that your the profit of your sensor owners as well as your SCSP will be increased in such a way that the requirement of the end user or the needs of end user are satisfied. So the existing schemes of pricing are available. However, there is no schemes for your sensor as a service. So this proposed architecture is responsible for providing optimal pricing for your sensor as a service. So this proposed scheme has basically two components. First one is pricing attributed to your hardware and pricing attributed to your infrastructure. So your pricing attributed to your hardware deals with the usage of your physical sensor node. However, the pricing attributed to your infrastructure is associated with the infrastructure that we are using. For example, the routers or the gateways which we are using to make the connection between your end devices and your sensor cloud. Now, what is the goal of proposing this pricing scheme? So the goal, as I have mentioned, is to maximize the profit of your SCSP, which is responsible for managing various services which are provided by your sensor cloud, maximizing the profit of your sensor owners who deploy their sensors, and maximizing the satisfaction of your end user. So this basically focus on maximizing the profit that is made by the same point, SCSP, optimal pricing of your end user, and end user satisfaction. Now the next topic is your fog computing. So fog computing or fogging is a term which is coined by your Cisco. So the idea of fog computing is to extend the cloud near to your IoT devices. It means to bring all the services which is provided by your cloud near to your end devices. So the primary aim of your fog computing is to solve the problem faced by cloud computing during the processing of your IoT data. Now, why the problems occurred during the processing of your IoT data processing? Since 40% of the world data came from sensors alone by 2020. 90% of the world data were generated only during the period of last 2 years. 2.5 quintillion bytes of data is generated per day. So in short, the data generation by your IoT devices is very heavy. So in order to manage that data, it is difficult for cloud computing to manage that such amount of massive data. So there is a need of an intermediate layer between your cloud and your end devices, which help the cloud to manage that data in real time. See, in case of the distance between your end devices and cloud is large, so in order to access the data from cloud, some latency will be added, and if the end devices need the data in real time, it will be difficult for your end devices to fetch the data in real time. So for that there is a need of a layer which is responsible for fetching the data. Now, why fog computing? As I have already told you that the ability of the current cloud model is insufficient to handle the requirement of your IoT data. So in order to handle that data, there is a need of intermediate layer which will solve the issues such as your volume, latency and bandwidth. First one is your data volume. So as I have told you that by 2020 about 50 billion of devices were online, and these devices are going to generate massive amount of data. In order to handle that data, it will be difficult for cloud. So presently billions of devices produce exabytes of data every day. Devices density is still increasing every day. Current cloud model is unable to process this amount of data. Since private firms, factories, airplane companies and various manufacturing industries are producing that much amount of heavy data. So current cloud model cannot store all these data, and in addition to that cannot provide that data on the request of the end user in real time. So that's why there is a need of fog computing. Next one is latency. So the time taken by a data packet for a round trip. For example, a round trip here means end user will request for a data, and the server or the centralized server or your cloud will provide that data to your end devices. So the time taken by the request to reach at the cloud, and the time taken plus the time taken by the data to reach at the end device from the cloud. So this is the round trip time. So in case of your cloud computing, you can see this figure. So in case of your cloud computing, so total time will be initially request will be sent to cloud, this amount of time, then some processing will take place at the cloud, and after that again the data will be sent to your end devices. So total time will be time to send the request, processing time plus time to send the data. So in case of your cloud, this time is large as compared to fog, because the distance between your end device and cloud is large as compared to the distance between your fog devices and your end devices, because fog devices are somewhere near to your end devices. That's why the time taken by time taken to send the request and time taken by the data to reach at the end devices will be decreased, right? So the overall time in case of fog is less as compared to your cloud. So this is a formula for your latency. So latency is the time from your device to cloud, then the time for the analysis, that is processing time, and the time taken by your cloud to send the data to the device. So in case of your cloud, the latency will be increased. When the action reaches the device, accident may have already occurred. So consider an example of your automated vehicles, right? In case of your automated vehicle, we need data in real time. So a delay of fraction may result in accident, right? So in order to prevent that, we need the processing or the data in real time. So in order to do that, we need the processing or the data near to the end devices. For that thing, fog computing is helpful. Now the bandwidth. Since in order to send the data from your cloud to the end devices and from the end devices to cloud, the requirement of bandwidth is large. However, in case of your fog computing which are near to your end devices, the requirement of bandwidth will decrease. Now, what are the requirements of IoT? So in case of your IoT environment, we need reduced latency of data. There are various applications of IoT which require data in real time in order to prevent various accidents, machine failures, and etc. 1 minute delay while taking decisions makes a huge difference, and also sometimes also leads to accidents, hazards, etc. Latency can be reduced by analyzing the data close to your data source. So in case of your IoT, we need some technology which will provide do the analysis of data near to your end devices. Second one is your data security. So the data which is produced by your end devices must be secured and protected from intruders. So that data must be monitored 24/7, because any change in that data may result in accidents also. So appropriate action should be taken before the attack causes major harm to the network. The next one is operation reliability. So the data generated from IoT devices are used to solve real-time problems. Integrity and availability of data must be guaranteed. Unavailability and tampering of data can be hazardous. Next one is processing of data at respective suitable places. So in case of your IoT, it is required to process the data near to your end devices, because every time we need data, it will not be suitable to fetch the data from the long distances, because in case of your IoT, there may be time sensitive data also. So a delay in fetching that particular data may cause hazards. Next one is monitor data across large geographical areas. So in case of your IoTs, we need to sometimes we need to monitor the data across large geographical areas. Now, when should we use fog? So if the data if we need to analyze the data within a fraction of second or in real time, then we need fog. If there are huge number of devices which are difficult for your cloud to manage, then we need fog devices. Third one is if the devices are separated by large geographical distance, then in order to prevent the latency, we need fog devices. Last one is if the devices are needed to be subjected to extreme conditions where each and every fraction of time is critical, then we need fog computing. Now the architecture of fog. So the architecture of fog consists of your IoT devices. The lowermost layer is your IoT devices, that is your end devices. Then the second layer is your fog layer, which consists of various fog nodes which will provide the fog services. Fog services are nothing, these are all the services which are provided by your cloud. However, these services are near to your end devices. And last layer is your cloud layer. So fog nodes are going to fetch the data from your cloud layer and provide that to your IoT devices within a fraction of time. Now, what should be the characteristics of your fog nodes? So your fog nodes should be able to store the data which is generated by your sensor, or should be able to cache the data which is provided by your cloud and required by your end devices. So in short, fog node should be able to provide storage. Second one is computing facilities. So your fog node should be able to process the data or analyze the data. So in order to provide various services to IoT devices, we need the fog nodes to process the data. So there should be some computing facilities which should be available at your fog nodes. Next one is your network connectivity. So these fog nodes, wait for 2 minutes, I'm coming. Yeah, we were discussing about the characteristics of the fog nodes. So as I have discussed that fog node should be able to provide storage. Fog node should be able to provide computing facilities. And third one which we are discussing was your network connectivity. So your these fog nodes should be able to connect to each other and also to your cloud as well as to your end devices to make the communication possible between various devices. So your fog nodes can be router, embedded servers, switches, video surveillance, etc. Depending upon the application or the network where we are using. So each fog node have their aggregated fog node. So what this means? So there are various fog nodes present. So there should be one aggregated fog node that will be that is responsible for handling the data of all these fog nodes, which again is connected to your cloud. Now working of fog node. Working of your fog computing or working of your fog nodes. So basically there are three types of data which is produced by your end devices. First one is your very time sensitive data which we need to process within a fraction of time. Second one is your less time sensitive data which may be processed within 1 or 2 minutes or depending upon the requirement. And third one is the data which are not time sensitive. So what fog computing do is the data which is very time sensitive. Now working of fog nodes, basically there are three types of data, very time sensitive data, less time sensitive data and data which are not time sensitive at all. So in case of fog, the data which is very time sensitive is processed at the fog nodes which are near to the end devices, that is your IoT layer, IoT devices. However, the data which is less time sensitive as compared to very time sensitive, that is the data which can be analyzed within few seconds or minutes, is not analyzed at the fog nodes. However, it is sent to the aggregated fog node which analyze the same data and further send back the response to the end users. And third type of data which is not time sensitive at all is sent to the cloud for analysis, and cloud can perform processing on the data and further send the response back to the end users. So on the basis of the data which is present, that it can be very time sensitive, that require very less amount of time for processing. The second can be less time sensitive, and the data which is not time sensitive. On the basis of the type of data, we perform analysis at fog, aggregated fog and the cloud. Now this table shows the difference between the fog node that are closest to the devices and fog aggregated node and cloud in terms of their analysis duration, IoT data storage duration and geographical coverage. So the analysis duration for fog nodes is a fraction of second, whereas for the fog aggregated node it may vary from seconds to minutes. However, in case of cloud it may vary from hours to weeks. Similarly, for IoT data storage duration, for fog node it is very transient. Then for fog aggregated node it may vary from hour to days. However, in case of cloud it may vary from months to years. The geographical coverage of fog nodes that are closest to the devices is very local. For fog aggregated node it is wider as compared to the fog nodes, and for cloud it is global. Now the advantages of fog computing. First one is security. So fog computing is responsible for providing better security. Fog nodes can use the same security policy Next one is low operation cost. So the data are processed in the fog nodes before sending to the cloud, which reduces the bandwidth consumption and result in low operation cost. The third one is reduces unwanted accidents. Since the data is processed and analyzed near to the end devices, which results in less latency in order to make the decision, which is responsible for quick decision making and results in less or unwanted accidents. Next one is better privacy. So every industry can analyze their data locally with the help of fog computing. They can store their confidential data on the local server rather than sending to the global server or centralized server. Then they send only the data which can be shared to the cloud, not the complete data. The next advantage of fog computing is business agility. Fog applications can be easily deployed according to the tools available. They can be deployed anywhere we need and can be programmed according to the customer's need. Fog computing also support mobility. The nodes which are the fog nodes are mobile in nature. They can either join or leave the network anytime. They are deployable in remote places and can be subjected to a harsh environment conditions such as sea, railway tracks, vehicles, factory floor, etc. The next advantage is better data handling. So, in case of fog computing, fog computing can operate with less bandwidth. Data can be analyzed locally, and fog computing also reduces the risk of latency. Now, the application of fog. So fog computing is useful in real-time health analysis. So the patient with chronic illness can be monitored in real time. The stroke patient or the data can be analyzed in real time. During emergency alerts, the fog computing is responsible for alerting the respective doctors immediately. Last one is historical data analysis can be used in fog computing to predict the future danger of the patient. The next application of fog computing is intelligence power efficient system. Fog computing is power efficient. It reports detailed power consumption report of every day and also suggests the economical power usage plan. The next application is real-time windmill and turbine analysis. So wind direction and speed analysis can increase the output. Data can be monitored in real time with the help of fog computing. The next application is real-time rail monitoring. So fog nodes can be deployed to the railway track, which results in the real-time monitoring of the track condition. For high-speed trains, sending the data to the cloud for the analysis is inefficient. Therefore, fog nodes provide fast data analysis and improve the safety as well as reliability. Next one is pipeline optimization. So gas and oils are transported through pipelines. Real-time monitoring of pressure, flow, compressor is necessary. Terabytes of data are created. Sending all this data to the cloud for analysis and storage is not efficient because network latency in such cases is not acceptable. Therefore, fog computing is a solution in such scenarios. Now the challenges which we face during the usage of fog computing. First one is power consumption. Since in case of fog computing, one extra layer is deployed in between your cloud as well as your end devices. So that layer consists of various devices which require power. So the addition of these devices results in automatic increase in the power consumption, because in case of your cloud there are only two layers which require power. However, in case of your fog computing there are three layers which require power. So automatically the summation of the power which is required by other devices deployed in various layers in case of fog computing is large as compared to the cloud computing. Next one is data security. So the data generating nodes are distributed. Providing authentication and authorization system for the whole node is not an easy task in case of your fog computing. Next one is reliability. So maintaining data integrity and availability for millions of nodes is difficult. Failure of a node cannot affect the network. Next challenge is fault tolerance. Failure of a node should be immediately fixed. Individual failure should not affect the whole scenario. So achieving these 2 points is difficult in case of your fog computing. Next one is your programming architecture. So the fog nodes may be mobile in nature. Nodes can connect and leave the network whenever necessary. So many data processing frameworks are statically configured. These frameworks cannot provide proper scalability as well as flexibility. Next one is real-time analysis. So achieving real-time analysis in order to minimize the latency is difficult. As well as it is difficult to monitor huge number of nodes in the fog layer. Now we will discuss the questions of week 9. So the first question is, OpenStack is a proprietary and a closed source software that you have to pay and buy. Options are true or false. So the correct option for this question is false, because OpenStack is not closed. However, OpenStack is an open source software which requires no payment. Now question number 2. Question number 2 is, in OpenStack, which of the following components take care of user authentication? Options are Nova, Origin, C is Keystone, and fourth one is none of the above. So the correct option for this question is Keystone. Keystone is responsible for providing authentication as well as user authorization. So it provides identity service to the users. Next question is, that is question number 3, is, you cannot ping your OpenStack instance from an outside network unless you connect your instance with the public network through options are router, firewall, repeater, load balancer. The correct option for this question is router. You are supposed to connect your virtual OpenStack instance with the public network with the help of a router, through a router. So correct option is router. Next question is, what is the primary service model for a sensor cloud? Options are hardware as a service, platform as a service, data as a service, and sensor as a service. So the correct option for this question is sensor as a service. So the primary functionality of sensor cloud is to provide sensor as a service. Next question, that is your question number 5. Sorry, is, you can run 2 logical computers, one Linux machine and one Windows machine, on the top of the same physical hardware through the use of. Options are sharing, scaling, virtualization, inheritance. So the correct option for this question is virtualization. So virtualization is the concept where you can use or you can make use of a physical hardware over multiple logical instances. Now next question. In sensor cloud, one physical sensor can be abstracted as multiple virtual sensors. State whether this statement is true or false. So this statement is true, because in sensor cloud, virtualization is the basic concept which is used. So virtualization allows the abstraction of one physical sensor into multiple virtual sensors. Next question, that is your question number 7, is, in a sensor cloud framework, the end users have to continuously worry about owning and managing the physical sensor devices. State whether this statement is true or false. So this statement is false, because sensor cloud supports the existence of multiple actors with end user concerned only with the application data and not the internal details. Now question number 8. Virtual sensor within a sensor cloud have communication interface with. Options are only the physical sensor below them, only the end user application above them, both physical sensor below and application above, and fourth one is neither the physical sensor and nor the application above. So this virtual sensor should be able to communicate with both the physical sensor as well as the applications. So the correct option for this question is C, that is both physical sensor below and application above. Now question number 9. Question number 9 is, which of the following is true? So option A is, in case of your traditional wireless sensor network virtualization is supported. However, in your sensor cloud, virtualization is supported same. B is in WSN, that is your traditional WSN, there is no virtualization. However, in case of your sensor cloud, there is virtualization. Third one is in WSN, there is virtualization. However, in sensor node, sensor cloud, there is no virtualization. Last one is in both WSN and sensor cloud, there is no virtualization. So in case of your traditional wireless network, there is no virtualization. However, in case of your sensor cloud, sensor cloud is based on the concept of virtualization. So the correct option for this question is B. That is traditional WSN, no virtualization, sensor cloud, virtualization support. Now question number 10th. An organization ABC wishes to have an environment monitoring parameter of a particular region, but does not have the resources to deploy its physical sensors. However, another organization B has some physical sensor that monitor the environment deployed in that region. Can sensor cloud help in achieving A's objectives? Options are yes or no. So the correct option for this is yes. So with the help of sensor cloud, A can achieve its objectives. Now question number 11th, referring back to question number 10th, based on your answer, determine the role of organization A and B in the given scenario. Option are A act as sensor owner, B act as end user, B option is A act as your end user, B act as your sensor owner, C is A and B both act as sensor owner, D is A and B both act as your end user. So the correct option for this is B, because A does not have their own sensors. It will utilize the sensor of organization B. So your organization B will act as sensor owner and organization A will act as your end user. So correct option for this is B. Now question number 12. Which among the following is a limitation of cloud computing? Options are on-demand services, virtualization, orchestration, large amount of computing and storage resources, additional communication latency for critical application. So the correct option for this is D, because in case of cloud computing, there is additional communication latency for a critical application. Now question number 13. In fog computing, the fog layer acts as intermediary between your data source and cloud for immediate processing of critical data. State whether this is a true or false. So this statement is true. Fog computing sits actually in between your end devices and your cloud layer. Now question number 14. So in question number 14, the one-way communication latency between your fog device and your end device is 20 ms. However, for your cloud it is 50 ms. Now the processing time of fog is 10 ms and for cloud it is 5 ms, that is millisecond. Now we have to find the difference between the overall delay which is faced by your cloud and your fog. So in order to solve this question, first of all we have to calculate the delay which is faced by cloud and the delay which is faced by fog. So the delay which is faced by your cloud is 50 for one-way communication, plus 50 for response, that is 100, plus the processing delay, that is 5 ms. So total is 105 ms. However, for fog it is 20 plus 20 plus 10, that is 50 ms. So the difference between 105 and 15 millisecond is 55 milliseconds. So correct option for this question is 55 milliseconds. Now question number 15. Which of the following is true? Fog computing acts as a complement to cloud computing. Fog computing is a replacement of cloud computing. Fog computing and cloud computing are the same. Fog computing is more powerful than cloud computing in terms of resources. So the correct option for this question is fog computing acts as a complement to cloud computing. That is option A. So that's all for this week. Thank you.